So I want to spend some time talking about graphs and graph analytics. So we've encountered these before in the context of the Elastic MapReduce assignment, but we haven't spent too much time in the lectures talking about them. But they're increasingly important in a data science context for reasons we'll talk about. So what is a graph? A graph is a pair of sets, a set of vertices and a set of edges. Okay, you might also see vertices referred to as nodes, but I'm going to try to avoid that terminology to avoid confusion with clusters of computers where each computer is referred to as a node. Okay, so V is a set of vertices and E is a set of edges, and each edge is a pair of vertices, a source and a target. And so edges may be considered directed or undirected, and we'll talk a little bit more about this, but maybe it's an edge from a source to a target, or maybe it's just a pair and the order doesn't matter. So these graphs are increasingly common in the wild, right? The web itself can be modeled quite directly as a graph where every page is a vertex and every link between pages is an edge. The internet underlying the web can be modeled as a graph where every computer is in a vertex and every route is an edge, or maybe even every packet. Social networks, as we've seen in some of the assignments, these are becoming increasingly important as a political driver and as a driver for social change. They're, the influence they have is pretty difficult to overstate, and this is very obviously a graph where every connection between two people in the social network is an edge. Communication logs can be modeled as a graph. Every phone call between two people is an edge, and of course in the news recently this is becoming quite important with the PRISM program. And so many more. And so one reason these are so ubiquitous is that it really does kind of get the fundamentals of communication, right? You have a big set of actors, and anytime one actor interacts with another, that can be modeled as an edge. And so this is just a very common paradigm that can capture the behavior of a lot of different kinds of systems. Okay. The other reason you see this to be so ubiquitous in kind of a data modeling aspect is that, objects and relationships between those objects, you can't really get any lower than that, right? So relations talk about, the relational data model talks about tables where you have records and attributes. But even here, there's a bit of complexity. You have to sort of think about a schema, and you have to sort of think about every record is going to have the same schema and so on. Graphs kind of blow up all that and disintegrate everything down to just objects and relationships. And so in some sense, it's a lowest common denominator data model. What we'll get into a little bit is my opinion that I think you throw out quite a bit when you sort of drop everything down to that level. But we'll talk about that in a bit. So what do we want to do with these graphs? So Bordaweckar in 2012 wrote a paper about analyzing analytics. So they tried to sort of categorize various analytics tasks in a variety of categories, and one of the categories was graph analytics. And he broke it down into these three patterns: structural algorithms, traversal algorithms, and pattern matching algorithms. And I think this is as good a breakdown as any other. So this is the one we'll use in the next several slides. So you think about just structural tasks, structural algorithms. The first thing to do when encountering a graph that you're expected to work with or understand is just to collect some basic metrics, right? How big is it? How many vertices and how many edges? And one of the takeaways I want you to have is that the number of edges is more relevant than the number of vertices when you're trying to understand the scale of a graph. So, many times you'll have a conversation with someone and they'll say, well, I have this really big graph I'm working with. So the next question you should ask is, how many edges does it have? Not how many bytes and not how many vertices. And the reason you don't care about the bytes is because there might be all kinds of other information packed into the labeling of these things, but that can really be factored out from the graph itself and modeled maybe more traditionally in a relational database. And so the performance may not depend so much on exactly the number of bytes. But the graph structure is a challenge, as we'll see. Okay, and so the number of vertices is one measure, but the number of edges is another. So why is the number of edges more important than the number of vertices? Well, because it scales quadratically with the number of vertices, right? You can have at most number of vertices squared number of edges, and that's a really, really big number in some cases, right? If there's 2 billion people using a social network, well, 2 billion squared is the number of possible friend relationships you have. And if you're expected to do some analytics on this graph, you're going to be processing all of those edges, perhaps. Okay. And then the second question you should ask after the number of edges is, what is the highest in-or-out degree as a proxy for really what is the degree distribution here? So what do I mean by degree? Well, the in degree of a vertex is the number of edges that are coming into it, and the out degree of a vertex is the number of edges that go out of it. Okay. And so how the edges are distributed among all the vertices tends to be a driver of how difficult the graph is to work with. If they're all pretty evenly distributed, then this isn't much of a problem. You can parallelize things, as we'll see, and everything works out nicely. However, almost never do graphs in the wild have this property where things are sort of randomly distributed. It tends to be very skewed. So there's sort of, in a social network, there tends to be a person who is friends with everybody in the graph, right? Very, very popular people, or almost everybody in the graph. Okay. On the web, there are pages that tend to be linked to by everyone, right? Very, very popular pages. And so this imbalance in the degree distribution is one of the challenges in working with very, very large graphs. And so if you know the number of edges, you've got one indication of sort of gross scale. And then if you know about how many edges are in the most popular vertex, that gives you some idea of how skewed things are. Okay. So fine. So when you're working with graphs, these are the things you're going to be able to do. Can you just count the vertices, count the edges? Can you say, given a vertex, can I get the number of in edges and out edges for that vertex? And can I maybe do that for every vertex in the graph? Okay. And so if this is hard to work with, this is going to be the basis for many other tasks. So one structural task you can do that's a little more detailed is to construct the histogram of a graph. And you saw this in the Elastic MapReduce assignment if you completed it. So we saw that the out degree of a vertex is just the number of outgrowing edges. So some notation, let's say for each integer d, we'll let n of d be the number of vertices with that out degree d. Okay, so for example, in this graph, we have, what is the out degree of this vertex? It's 0. There are no outgoing edges. The out degree of this vertex is 2. There are 2 outgoing edges. The out degree of this vertex is 4. There are 4 outgoing edges. So now we can count them up. We can say, how many vertices in this graph have out degree 0? Well, there's just one. It's this one. How many vertices in this graph have out degree 1? Well, there are 3 of them. This one, and this one, and so on. And then you just plot d versus n of d and create this histogram. So we see 1 vertex at 0, 3 at 1, 2 at 2, and so on. Okay. So why might this be a good idea to do? Well, it tells us something about the graph we're looking at. So if we see this kind of a pattern, so we might see this kind of a pattern where very many vertices in the graph have a very small out degree, and fewer as you go out the x-axis. Or potentially you could see this other pattern where very few have a small out degree and many, many more have a high out degree. So this is a much more connected graph, right? Everybody tends to be connected to everybody else in this case. Most people have a very high out degree. Most vertices have a very high out degree. And here, very few have a very high out degree. Okay. And it could be sort of more mixed like this. It could be sort of bimodal. So what's going on here? Well, if we see this pattern, then you can model this as an exponential distribution where d is in the actual exponent. And what this tells you is that it becomes very, very unlikely, the further you go out the x-axis, it becomes exponentially less likely to find a vertex that has that out degree, right? So most have a small out degree, one or a few, and as you go further out, it's much less likely. Okay, and so you can see this effect very clearly if you plot it with on a log scale. It becomes linear on a log scale. Now, the thing about this distribution is a random graph has this distribution. So what do I mean by a random graph? Well, this is take a set of vertices and then choose 2 vertices at random and connect them with an edge. Then choose another 2 vertices completely at random and connect them with an edge, and so on. If you follow that process, you'll get this kind of a distribution of the connectivity, right? There'll be it's very, very unlikely to construct a vertex that is connected to lots and lots of other vertices using this process. Okay. So fine. So it turns out that you don't find random graphs in nature very often. Okay. That's unfortunate because if you did have a random graph, it's actually fairly easy to work with. And by work with, I mean implement some of the tasks that we'll be talking about, say, in parallel, because you can split the edges up across a bunch of different machines and just work with them all sort of independently. But what you see more often in practice are these power law distributions, the zip distribution, where there's some x that's in the exponent. You're raising the degree d to that exponent. And human-generated data tends to have this distribution. And if you think about it, there's at least one way to get to build some intuition for why these come about. Okay. So instead of choosing two vertices at random and connecting with an edge, instead, when you choose a vertex to connect with an edge, favor those ones that are already well connected. Okay. So why would you bother, or why would this happen sort of naturally? Well, think about it. If you're in a social network and you have someone who joins Facebook for the first time, are they more likely to connect themselves to someone who's already very popular, or are they more likely to connect themselves to a bunch of people who don't already have lots of friends? Well, it's much more likely to connect yourself to someone who's already very popular. That might be who introduced you to Facebook in the first place. Or with Twitter, are you more likely to follow people that already have a lot of followers, or more likely to follow people that do not have a lot of followers? Well, more likely you're going to connect to and follow, you join Twitter in order to follow popular people. Okay. You can also think about this in terms of maybe the internet or the web. When you create a web page and put it on the web, are you more likely to link to sites that already have a lot of links or not? Okay. And the answer is you're more likely to connect to, it's reasonable to say that you're more likely to connect to web pages that already have a lot of links. Okay. So with this preferential attachment model of constructing graphs, you'll generate this Zipf-ian power law distribution. These are the distributions you tend to find in nature or on the web, whether you call that nature or not. And they have a distribution like this. They have this fatter tail, this long tail. So now it's not quite so unlikely to find vertices that have a very, very, very high out degree. Okay. And you can see this effect more clearly on a log-log scale plot where both axes are on a log scale. I think I'm not a huge fan of using log-log scale except very sparingly because lots of distributions end up looking linear on a log-log scale, but these are defined to be linear on a log-log scale. So you can do this kind of structural analysis. You can construct this histogram of very large graphs like the web, which Broder et al. Did in 2000, and we're probably overdue for another analysis of this type, but it's become computationally pretty difficult to produce these kinds of plots for the current internet. Okay, so here's the plot, here's the histogram of the web, and the question is this an exponential or is this a Zipf-ian power law distribution? And you can see it's kind of here in the description, but it's pretty clearly a power law. This is a log scale axis, and this is a log scale axis, and this looks pretty linear. So what the authors went on to do, which I think is pretty interesting, is produce this kind of schematic of the overall structure of the web. And this circle in the middle here is a big, strongly connected component, meaning that the pages within that component, if you can reach X from Y, you can reach Y from X for any two pages. Okay. But then there's also an in and an out set of vertices, pages, that are kind of about the same size as the strongly connected component. So these are things that are, you can reach the strongly connected component from these, but you cannot reach back from the strongly connected component. So they link into the main mass of the internet. Okay. And then similarly on the outside, there are things that link from the strongly connected component, but you can't get back. And it's about these big 3/3. And then they pointed out that there are indeed tubes that connect the in to the out directly, not going through the strongly connected component. And there are these tendrils that sort of go off nowhere, but these are perhaps minor components relative to the main three. And then you also have these sort of disconnected components that are smaller. But this is sort of interesting to understand the basic, physiology of the internet, and it's, again, difficult to produce this now. So what are some more sophisticated structural analytics tasks we can do with a graph? Well, one is to find the diameter of the graph. So this is the longest of all the shortest paths in the graph. So what's the shortest path? Well, given a vertex X and a vertex Y, find all the different ways of reaching Y from X and take the shortest one of those. That's a shortest path. Now do that again for all possible pairs of vertices in the graphs. The longest of all those shortest paths is the diameter. And so intuitively what this is measuring is, the width of the graph. What's the longest sort of path you have to take to get from one place to another? Okay, and this gives us a measure of how much work we have to do when we're traversing the graph. Okay, so if everything is very tightly connected, then the diameter will be very short. Right, it only takes a few hops to get from anywhere to anywhere. And if the diameter is much longer, then it could potentially take longer than that. So this gives you kind of the 6 degrees of separation, 6 degrees of Kevin Bacon sort of measure. Fine. So what is the diameter of this graph here? Well, we're looking for shortest paths. So let's look at some possible candidates. Well, things like A to F and A to B and D to C are all going to be shortest path 1. So let's look a little closer at ones that appear to be far apart on the page here. So A to C, what's the shortest path there? Well, one path is A to B, B to E, E to G, and G to C, and that's a path of length 4. But there's a shorter one. There's A to B, B to D, and D to C. And so A to C, the shortest path is 3. So let's look at other ones. Well, F to anywhere, well, you can't reach anywhere from F because all the edges point inward. And we're assuming a directed graph for this particular exercise. And G, similarly, you can't get anywhere. You can get to C, but C you can't get anywhere except back to G. So it looks like, starting back from A to G, how many hops does it take to get there? 1, 2, 3. So A to G is 3. And that should be the longest ones. So the diameter of this graph is 3. So we can also measure the connectivity coefficient of a graph as a structural analysis task. So this is the minimum number of vertices you need to remove that will disconnect the graph. And so you can think of this intuitively as a measure of the fragility of the graph, right? How much redundancy is built into it. So if you're designing a network and it turns out the connectivity coefficient of the graph is 1, that means that potentially if one machine goes down, you could partition the network where nobody can communicate. Okay, so if you're an advertiser, you might be interested in the connectivity coefficient of a graph. If you're trying to reach as many people as possible, it could be that if a few people don't pay attention to the ads, then a whole bunch of other people won't send the message if you're sort of in viral advertising or social media advertising. Okay, and so remember in the CAP theorem that we discussed in the NoSQL lectures, P was partitioning, right? So this was if your system becomes partitioned, if your network becomes partitioned, can the systems still function? And so connectivity coefficient could be a measure to help you estimate how likely it is that your network is going to be partitioned. Okay, so what is the connectivity coefficient of this graph? Well, it depends on exactly what we mean by connectivity first. So we can say that two vertices x and y are strongly connected if x is reachable from y and y is reachable from x. Okay, and we might say that they're just connected if x is reachable from y or y is reachable from x. And so this is sort of equivalent to ignoring the directionality of the edges. So if we just assume that everything's undirected, then we'll be using the second definition. So let's assume that for a second. Let's assume we just mean connected here. Well, look, if we don't care about direction of traversing, then if we remove E, is the graph disconnected? No, because you can still reach everything through this other edge up there. And so the only node here that appears to not be redundant here is B. And so if you remove B, though, you'll have two partitions in the network, A and F, and all the other ones here. So the connectivity coefficient of this graph is 1 because we can find a vertex that if we remove it, it'll be a partition network. Okay. And so we already discussed why you might want to compute this. So the connectivity coefficient is a measure of the graph itself and doesn't really give us a way to understand the relative importance of an individual vertex. And so for this purpose, there's been various notions of centrality defined. So one is the closeness centrality of a vertex, which is the average length of all the shortest paths that pass through it. Right? So this, intuitively, you can maybe compare this with the diameter of the graph. Right? If the diameter is long and the average length of all the shortest paths that go through a particular vertex is short, then it's not part of the diameter of the paths that define the diameter of the graph. And so in some sense it's maybe less central or less important. Okay. So another is maybe more common is the betweenness centrality of a vertex. And this is the fraction of all the shortest paths in the whole graph that pass through this vertex, right? So if you need to go, all roads lead through Rome, right? If you need to go from Seattle to Atlanta in the U.S., then perhaps all paths go through one of two different major highways, or maybe one or two cities, the northern route and the southern route or something. And so the betweenness centrality of these two intermediate hubs is high. And so if you think about a public transportation system where all trains lead into some central hub and then go out again, that central hub will have a high betweenness centrality because the shortest path to get from point A to point B always goes through this one central vertex. Okay. So what is the betweenness centrality of vertex E in this case? Well, there's a shortest path A to B to D to C that we found. The shortest path from A to C goes through there. And the shortest path from A to G, A, B, E, G, is 3. So if you sort of add all these up, you'll see that E is only involved in A, B, E, G, and then a bunch of ones that are rooted in E itself, E to C and E to G. So the betweenness centrality of E is 3. Oh, sorry, 3 divided by the total number of shortest paths in the graph. Okay, it's a fraction. So we talked about a couple different notions of centrality, and one more is degree centrality, which is just the degree of a vertex divided by the total number of edges, right? So this is the fraction of all the edges that touch me. Okay, and so maybe this is a good candidate for our, we're seeking some notion of importance of a vertex in a graph. All right, so imagine we have a social network, and then the degree of a vertex is the number of friends you might have. Well, people with more friends are in some sense more important than people with fewer friends in the context of a social network. Fine, but if, say we both have 5 friends, well, then we have the same degree centrality by this definition, but what if your 5 friends are, they themselves, much more connected than my 5 friends? In some sense, you should be more important than I am in the context of this social network. And this notion of degree centrality doesn't capture that. All right, so let's see if we can improve on this. Well, another notion of centrality is eigenvector centrality, which is actually just PageRank. And so if you are familiar with PageRank, or this may be another way of looking at it, and if you're not familiar with PageRank, then this is a great way to develop an intuition for it. So the basic idea for computing PageRank is, while things are not converged, for each vertex in the graph, compute the rank of that vertex by adding up the ranks of all of its neighbor vertices. Okay. All the incoming edges if we assume a directed graph. Right? So this allows you to say, well, look, if Barack Obama, if the President of the United States is connected to you by one hop, is your friend, say follows you on Twitter or something like that, well then you're more important than somebody who doesn't have such an influential person in the graph. You add up the rank of the president to your rank. Okay. Meanwhile, you distribute your rank to all your friends, right? So, and you repeat this passing of rank, of weight, of importance across the network, across the graph, until you reach some convergence condition. And then that convergence condition gives you a relative score of who's more important than who, perhaps. Which vertex is more important than which other vertex. But there's a couple of problems with this approach. So one is, one page or one person in the social network with millions of outgoing links, if they link to me, that's somehow less valuable than a page that only links to a few people, right? So if you've got one of these crawlers that follows everyone in order to collect as much, follows everyone on Twitter in order to collect as much data as possible, it's not very important that they follow you, right? You don't consider that to be very prestigious that you have some automatic robot crawler following you. Meanwhile, if you have an aggregator page that sort of links out to everyone on the internet, similarly, that's not very important that it links to you. So somehow you want to make sure that they divide their rank amongst all their outgoing edges, as opposed to just give their total rank to each outgoing edge. Fine. So that's easy to fix. Another notion here is that, well, if I'm 27 hops away from Barack Obama, that's less important than if I'm 1 hop away. And so we really shouldn't count that as very influential. And so we need some sort of a damping factor that as you get further away, it sort of lowers the importance. Okay. So you combine these two notions together and you get the definition of PageRank as it was published. And there's a couple of variations on this, but this is the one to know. Okay, so while not converged, the rank of vertex A is the sum of all the ranks of the vertices that link to A, but each one is divided by the total number of outgoing edges. So in this notation, we assume that there are edges B linking to A, C linking to A, D linking to A, and PR of A, the page rank of a node of a vertex X, is going to be the page rank of the vertex X. L of X is the number of outgoing links from X. And so for the page, we take the page rank of B and divide by the number of outgoing links away from B. Take the page rank of C, divide by the number of outgoing links away from C, and so on. Add all that up, and that's all the contribution to A. And then we multiply by a damping factor to make sure that what we pass on diminishes over time as we get further and further away. And then this other term in this expression is just to ensure that all the ranks sum up to 1, so that we can sort of interpret them as probabilities. And in fact, you can directly interpret this as a probability, which is another way of looking at PageRank and deriving PageRank, is to take random walks around the internet, around the graph, right? So you start on a random vertex and just start walking, make a choice at random among the edges, the outgoing edges, and just traverse around. Well, if you do this a bunch of times, you can derive how likely it is that you'll spend time on some particular vertex versus some other particular vertex, and that will exactly be the PageRank. And so this is sort of, all roads lead back to Wikipedia or CNN or some other very, important vertex in the web graph. So that's PageRank, and what I wanted to point out before we move on is just the relative simplicity of this, right? It really comes out of an intuitive notion of trying to figure out how can we measure the importance of a vertex in the graph. And so, you start from very simple notions of, well, maybe important means just the one with the highest number of edges that link to it. Well, there's some problems with that, so let's see if we can fix it. Maybe it's the one with the most number of paths that go through it. And maybe we don't care about all paths, we care about shortest paths. So that gives you another notion of importance. And you say, well, that's got some problems too. What are the properties we really want here? Well, maybe it kind of captures, the importance of your friends needs to be added in there somehow. And you can sort of walk through this and come up with where PageRank came from. So the way it's presented, just like a lot of these things, are presented in terms of a finished formula, and then you kind of have to work out back, reverse engineer where it came from. But a lot of these things are developed very intuitively, and the formula is only used as a notion to express the intuition in a precise way. So we talked about structural analytics tasks as broken down by this paper in 2012. What are some examples of traversal tasks? So one is to find the minimum spanning tree of a graph. And so that is the smallest subset of edges that connect the graph by some notion of connectivity. So if we ignore directionality, we can talk about weakly connected graphs. So what is the minimum spanning tree of this graph? So we're looking for the smallest set of edges, a minimum spanning tree of this graph, because there might be many that have the same number of edges in them. A minimum spanning tree of this graph. Well, we can get from A to B, and again, we're going to ignore directionality, so there's actually 2 edges from A to B. So we take one of those. Then we can get from B to F, and we can get from B to E, and we get to B to D, and then we get from D to C and E to G. And so that's 1 edge, 2 edge, 3 edge, 4 edge, 5 edge, 6 edge. And so the minimum spanning tree, the number of edges in the minimum spanning tree is 6. Another way to get 6 is go from A to B and A to F, and then the same otherwise, B to D, B to E, D to C, and E to G. Okay, so there's 2 different minimum spanning trees with the same number of edges in them. And there are fast algorithms to compute this that we're not necessarily going to go into. So this is sort of a guided tour of various tasks you might want to compute, but we're not necessarily going to describe the algorithms in every case. All right. So another traversal-oriented task is finding paths and circuits. And so the classic example of this is Euler's bridges of Königsberg problem, where the task is to find a path where we visit every vertex and yet cross every bridge in this graph here in the picture only once. And so the observation that was made here was, well, if you enter by a bridge, you must also leave by a bridge. And you can't leave by the same one you came in on because that's the definition of the problem. So this suggests that there needs to be an even number of bridges to every vertex, right? You have to have one to come in on and one to go out on, and then you can come back to this vertex as many times as you want. And so there's two sort of related results here. If you, going from the bottom one here first, if you actually want to start and end on the same vertex, well, the condition is that every vertex in the graph needs to have an even number of edges so that you can come in by one and you can leave by one. And this allows you to make an entire circuit all the way around the graph. If you don't care where you start and end, you're allowed to start on one and end on another, then it's a little bit softer condition. You can, most of the vertices need to have an even number of edges, but you can have at most two vertices that have an odd degree, the one you start on, the one you end on, because you'll need to leave by one, you only need to come in by one. And I'm assuming undirected edges here. The definitions get slightly more complex if you talk about directed, but not much. Essentially, you need to have a balance. You need to have the same number of in-degree edges and out-degree edges. Okay. And so what's nice about this is this is a great result because it's very easy to check this condition, right? You can just add up the degrees of all the vertices in the graph, and you can tell whether one of these circuits or one of these paths exist. But to sort of demonstrate the subtlety of some of these graph theoretic problems, if you make a very slight change to the problem statement, the answer becomes a lot harder. So can we create a path that visits every vertex only once as opposed to every edge only once? Well, this is a hell of a lot harder. And the reason is that intuitively, if you think about it, every vertex has lots of edges, and so it's involved in lots of different paths, lots of different possible paths through the graph. And you're trying to find one of these such paths that touches every vertex only once. Well, given that this vertex is involved in lots of different paths, you're only allowed to use that vertex one time. And so you can imagine that it's difficult to figure out what is the best way to use this vertex. There's a whole lot of different conditions you have to consider. Okay. A related problem is, assume there's a cost to traversing each edge, right? There's a distance you have to travel, for example. Can we find a path that visits every vertex only once, but also has the minimum cost out of all these? And so there's no efficient algorithm that can exist for these problems, and so heuristics and approximations are the best we can do. And this extension here is the traveling salesman problem. Okay, so these might be some of the tasks you might want to do. These actually come up, I would argue, less often in a big data context, especially this one, in part because it's such a difficult answer to compute. And also, it's not clear that it's all that useful, say, in a social network context or in a web analytics context. You're not necessarily trying to find paths that touch every single vertex in the entire web. So this tends to be, the only times when you're interested in touching every vertex in a graph, I'll claim, is when the graph is in some sense small. Okay. So this is less of a big data problem, but it's something to be familiar with if you're thinking about graph analytics. All right. All right, so one more traversal task, just to be familiar with, is maximum flow problems. So here the input is a graph with labeled edges indicating the capacity at each edge, and then special vertices, sources, and sinks. And the idea is to find a subgraph that maximizes flow between sources and sinks. And so the observation here is that for each vertex, incoming flow must equal outgoing flow. Okay. And so in this example, if A is a source and F and G are the sinks, then you can think about a subgraph where you just have A directly to F because it's only one hop away. And so the flow between them is 2. But if you look at a path A to B and then B to F, you get the flow of 4 here and the flow the capacity of 4 here and a capacity of 3 here, which means the maximum flow along this is 3, right? There's some unused capacity on this edge, but 3 is still higher than 2, and so we want to include that in the subgraph from A to F. Okay, and then to get it over to G, you can do sort of a similar walk and say, well, one path is B to D through a capacity of 5, and D to E through a capacity of 2, and E to G through a capacity of 2. And so the maximum flow here is 2, while A to B, B to D, D to C, and C to G, the maximum capacity is 3. This edge is the weak link. Okay, so it looks like the max flow subgraph is ABF, DCG, or rather the edge AB, the edge BD, the edge DC, and the edge CG, and the edge be F. All right, so the final category of graph analytics tasks are these pattern matching tasks, and this is where we want to maybe spend a little bit of time, especially because they're somewhat relevant in the news lately with this PRISM system, and I'll try to touch on that in a bit. Okay, so here the idea is to find all instances of a particular subgraph pattern. And so a very simple subgraph here is two vertices that both connect to each other. Okay, and so here you may have conditions on the vertex labels or on the edge labels in order to more precisely specify the exact pattern you're looking for, but you're looking for all instances of this pattern across the graph. Okay, so how many times does this pattern appear in this graph, or what are all the instances in this graph? How can you instantiate this pattern there? Well, here's one from A to B. You instantiate $x equals A and $y equals B, and that seems to fit. And then G to C seems to fit. $x equals C and $y equals G. And then actually, if we're not careful, you have, or perhaps this is what you want, but generally you don't, you'll have duplicates of this, where $x can be B and $y will be A. Whoops. A will be A, and $x will be G, and $y will be C. So there may be 4 instances of this pattern, only 2 of which are in some sense unique. So a popular pattern matching problem is to find the triangles in a graph. And so a triangle is a sequence of 3 vertices that are connected to each other. So A connects to B, B connects to C, and C connects back to A. And so the total number of triangles is a measure of connectedness. There's lots of algorithms to compute this measure, to count the number of triangles, and it's a popular challenge problem, kind of benchmark for computer scientists to compare different systems and compare different algorithms. Its utility in practice as far as actually analyzing, getting information out of a graph is not been made so clear to me when I talk to people who compute this. It seems to be more of a good benchmark problem for systems as opposed to a actually informative measure for social network analysis. But that doesn't mean, that's not to say that it's not used ever. So for that reason, I'm not going to go into a lot of detail in the algorithms here, but a key idea to remember here is that a naive algorithm will actually find the same triangle 3 times, right? Connects to B, B connects to C, and C connects back to A, and then B, C, A, B, and then C, A, B, C are all logically the same triangle in that they involve the same nodes, but if you're not careful, you'll find all of these, and so this gives an opportunity to come up with much faster algorithms. I think the other reason why it's studied in a lot of detail is that it's perhaps the simplest possible pattern you can find, and so it's a good starting point to do more complicated pattern analysis. And in fact, the pattern analysis problem in general is a very difficult problem. It's a very expensive problem, which leads to a bunch of approximation techniques. And in fact, even for triangles, there's a variety of algorithms that don't count the exact number of triangles, but give you a good approximation with certain bounds. Okay, so this is a very rich area of research. But I think probably you'd be more interested in the pattern matching problem in general. Okay. And also maybe I'll point out that you can extend this notion to cycles that involve more than 3 vertices, and things change a little bit, but some of the techniques stay the same. So let's look at another pattern match example. This one's a simplified version of a real example that comes from work with some of our collaborators. Okay, so here, given a graph with edge labels is the extension we're going to make. Instead of just source node, source vertex, and target vertex, we're going to assume that there's going to be a label on that edge as well. So a third attribute in this table, if you will. And we're going to be looking at what this label represents is relationships like an object, someone knows someone else, and in this case, drug X interferes with drug Y, and so that label is interferes. So you sort of know what the relationship is, instead of it being a big anonymous relationship, or say in the case of Twitter where you assume that all the relationships are the same, it's just follows, or in Facebook every relationship is just friends, or in the web every relationship is just links to. This one now there are multiple different relationships being coded in the same graph. Okay, and so this is a slightly more realistic case when you're trying to do real data analysis. All right, so here we might say that drug X interferes with drug Y, and drug Y regulates the expression of gene Z, and gene Z is associated with disease W. And so now maybe one pattern that we want to look for is find all drugs that interfere with some other drug that is involved in the treatment of some disease. Okay, and of course you could put other restrictions on here too, or maybe you're looking for a specific disease, or you're looking for a specific drug. But now we're just looking for all patterns of this type. Okay, so pictorially, the query maybe looks like this, where we want to find an edge linking two vertices that's labeled with interferes with, that's then connected to where one of the outgoing edges of that vertex Y is connected to a vertex Z through an edge labeled with regulates, and then that vertex Z is connected with a vertex W that through an edge labeled with associated with. Okay, and we want to find all instantiations of this pattern. All right, so I'm not going to yet talk about algorithms to do this. I want to talk more about languages to express this pattern. And some of you with a database background may already be thinking about how you might do this in SQL, and that's one of the examples I want to show. So the first pattern language I want to consider is Sparkle, which is a query language derived, sort of SQL-like, derived in association with this resource description framework. And you worked with some of this data in the Elastic MapReduce assignment if you completed it. So resource description framework, RDF, defines a formal data model around the idea of triples, which are really just edges in a graph, labeled edges in a graph. And so logically you can think about a table with three columns: subject, predicate, and object. And the subject column refers to vertices in the graph, and the object column refers to vertices in the graph, and the predicate is the edge label. Okay. And so there's a lot of work that went into the formal model to define this, but I think it's most useful just to think of it as a labeled graph. All right. And so the query language ends up looking like this, where you can say select variable names where, and then define these triple patterns. And in this case, all the triple patterns look similar in that they all instantiate the predicate with a actual literal, and all the vertices are variables. But you don't have to do this. You could have a variable in place of the predicate, and you could have literals in the place of the vertex representations as well. Okay. So this says, give me all the x's such that x interferes with y, y regulates z, and z is associated with w. And so if this was actually our data set, then we might return this invented drug named Terrazine, because we can trace a path. Terrazine interferes with Betamin, Betamin regulates this gene, and this gene is associated with this disease. Okay. And there might be, billions of these triples. Let me give you another example of a pattern expression language that comes up in database courses in computer science, but is less often seen in industry, although it's starting to make a comeback, which is one of the reasons why I want to mention to you, make sure you're aware of it. Okay, so it's called Datalog, and it's based on a logic programming sort of paradigm, but simpler than general purpose logic programming languages such as Prolog. Okay, so here, to express our query in Datalog, we assume a relation R, which is just the same structure as the triple table we saw for Sparkle. Okay, and I'll show you another formulation in the next slide. So here the pattern, the syntax here looks not all that different than Sparkle. For each predicate, we have an instance of R, and we are looking for, give me all the x's such that x interferes with y, y regulates z, and z is associated with w. And we use three instances of this relation R. And it's essentially can be interpreted as a join. In fact, that's literally how it's going to be implemented in most Datalog systems. Okay, so you're going to join R on y equals y, join R again on z equals z, and then return the instantiations of the variable x. Now, so you've got a relation R with three attributes. Why can't you query this in SQL? And there's no reason. You can query it in SQL. So you can imagine loading this table into a database and rewriting this query like this, where you say a three-way join on the relation R, and I've given them aliases here, I for interferes with, R for regulates, and A for associated with. Then for each one of those relations, make sure you filter to the tuples that correspond to the predicate you're interested in. So make sure the I tuples are only those tuples that have the predicate equal to interferes with, and so on for regulates, and so on for associated with. And then you have to add a couple of conditions for the join. Make sure that the object of the I relation is equal to the subject of the regulates relation, and make sure the object of the regulates relation is equal to the subject of the associated with relation. And then finally just return the subject of the interferes relation. So all these things are equivalent, and that's one of the points I want to make, but I'll come back to that in a minute. So we implemented this query in 3 different pattern languages, and the fact that we could do so suggests that there's something in common between them all. And in fact, there is. What it is the relational algebra. And this is one reason why I've been trying to hit this throughout this quarter, is that, you know, if you put your relational algebra goggles on, the whole world starts to look like relational algebra. And you can start to see that these languages are not really all that different, and you can kind of look past the details of the syntax and see that what's actually going on is a relational algebra expression. So in this particular case, that expression might look like this. And I say might because this is not necessarily a rigorous statement here on the slide. So there's 2 joins, as we saw, 3 instances of the relation R, and this symbol means a select condition, where we're selecting for the predicate P equals regulates. And here the predicate P equals associated with, and here the predicate P equals interferes with. So now we have just the tuples that have the predicate with interferes with, just the tuples that have the predicate equal to regulates, and just the tuples that have the predicate associated with. And then we just do the join, where the object of this one equals the subject of this one, and the object of this one equals the subject of this one. All right. And so this, you know, if you look back on the earlier lectures, we talked about relational algebra. I hope you can convince yourself that this will produce an equivalent result. Now, as we said with the relational algebra, this is actually a specification of the order in which the operations should apply, while the other languages was more of a declarative expression of what the result should be, but not necessarily how to get the result. And that's generally the difference between the algebra and these languages. One of the benefits these languages give is they try to put aside any specification of exactly how it should be implemented and just specify the conditions that must be true of the result. And that's what we mean by declarative languages. All right. So fine. Maybe all 3 of these languages are equivalent, but I'd argue they're not. There's a benefit to the SQL implementation and the Datalog implementation, which I'll try to motivate by rewriting the query in a slightly different way. So imagine now, instead of having one big table called triples or called R with all the edges in the graph, imagine you had 3 different tables that came perhaps from different sources or different databases that you would combine together into one database. And each one of these tables represented different parts of the original graph. So you had an drug interaction database that had a relation interferes with, and just with 2 columns in it, you know, where the semantics of each tuple was the drug in the first column interferes with the drug in the second column. And from a completely different database, you had a facts about what drugs regulate which genes. Perhaps this was mined from the scientific literature. Perhaps this is derived from one of these public databases where some of this information is tracked, and so on. And then third, you might have a different database associated with or recording what genes are associated with which diseases. And so this is a very likely scenario, I claim, and in fact, again, this is derived from an actual example we have from working with our collaborators, and it's very much true that these different kinds of relationships came from different sources. And so it's actually more likely for you to have them in this form than it is for you to have them as one big graph. You actually have to do some pre-processing to merge them in together as one graph. But until you do that merging, you can't use that SPARQL language. And in fact, you can't use any graph language, and you can't really use any graph database, right? They only work on graphs. And so while it's a very general data model for capturing arbitrary relationships, it's not clear that the world is always represented as graphs in its source representation. It's represented as a bunch of tables that happen to have graph edges encoded in them. And so being able to work with them in the original format is a strength. And you can do so in, say, Datalog. So here, the query actually gets a little bit simpler. You have a join between these 3 separate relations, and you no longer have to sort of query on, specify the predicate that defines each one. Okay, and that's perfectly fine. If you have a mix of graphs and relations, you can handle both with Datalog. And in fact, you can process them the same way as you would any other query with the relational algebra, with your implementation of the relational algebra. Similarly, in SQL, SQL has no problem with expressing this query if the data was represented in this form. You would do a join between these 3 tables, and you just have the join conditions, and the query actually gets a little bit simpler. So I guess what I want to bring home is that graphs tend to not appear in the wild isolated, right? They're not sort of free ions. They tend to be, applications tend to be hybrid. They have some tables, they have some relations, and they have some graphs. And being able to work with both of them uniformly is an important strength. And so I think this emergence of graph-specific systems, while it does suggest that there's performance issues sometimes with modeling these traditionally as relations, and that's one thing we'll talk about in a couple of segments, it's not clear to me that capturing the entire world as a big flat graph is necessarily the right thing to do. It seems like you want a model that can do both, relations and graphs, and sort of interchange between them. Okay. Make one more point about Sparkle before we move on to some more complicated examples. So summarizing what we sort of said, while Sparkle is designed for graph query, there's a few problems that I want to point out. One is this notion of algebraic closure that we brought up when we talked about relational algebra. So the input is a graph to Sparkle. You can query a graph, but the output, if you go back to the slide on Sparkle and you look at the result, it's actually a list of records. It's no longer a graph. It doesn't have to be these triples anymore. And so therefore, I can't take the result of one Sparkle query and then again query it with Sparkle. The only thing I can query with Sparkle is a graph. And so one way to say this, and maybe is a little bit pedantic, but is more technically correct, is it's not algebraically closed. It returns a different type of thing than it takes as input. But this is a big disadvantage, as we've seen, right? You want to be able to chain queries together whenever possible. This is what gives you a foundation for features like logical data independence, which we argued back in the relational lectures as a really critical feature. Okay. Second, I'd argue that there's actually limited expressiveness, and we'll see some examples of this in a little bit, but you can't do these graph traversal tasks that we talked about. Most of these you can't express in Sparkle. Since version 1.1 in Sparkle, there is support for these path expressions that can express some forms of traversal, but it's not clear that all the general recursion is supported. Right. And you need general recursion, you need general graph, in order to implement these graph traversal tasks, you need some way of sort of walking over the entire graph as a whole, and Sparkle doesn't necessarily provide that. Okay. And then as we just pointed out in the last slide, if your input starts off as tables, before you can even touch it, you have to shred it into triples and model the whole world as a big pile of graph edges. While what's nice about graphs is you can actually do that. There's always a way to sort of shred it into a graph in some form. But the process of doing that might blow it up by a factor of 3 or a factor of 6 is what we see in practice, depending on exactly how you model things, and depending on what your table structures look like. But this is, a tough hill to climb, to try to recover that performance that you give up just by shredding it into a graph. So again, I think what this tells me is that we want a system that can handle both graphs, can express graph traversal tasks, which SQL is not great at, and we'll talk about that in a moment, but neither is Sparkle, but can also work with tables in whatever form they're in. Okay. So these graph pattern search problems were in the news in June 2013 pretty heavily, associated with this PRISM system being developed by the NSA. And so an article in Business Week described the kinds of tasks that they're interested in doing. And by the way, the technologies that they're using in this are things you've heard about, or as far as we understand. So the system Accumulo I mentioned in the NoSQL lectures was actually developed by the NSA and then released open source and then commercialized after that. And that's kind of the underlying platform. And then the kinds of applications they want to do using this Accumulo system and other systems are of the type that we've been describing in terms of pattern search. And so let me give you an example of that. So in this Business Week article, they talk about, in October, a foreign national named so-and-so purchased a one-way plane ticket from Cairo to Miami where he rented a condo. Then over the previous few weeks, he had made a number of large withdrawals from a Russian bank account and placed repeated calls to a few people in Syria. And more recently, he rented a truck, drove to Orlando, and visited Walt Disney World by himself. And the point they wanted to make in the article is that individually, none of these activities would raise any flags, but collectively they might. They might be worthy of closer inspection. And whether you agree with this or not, I mean, maybe you'd say that this does not warrant further inspection, but just trying to state the facts of what of what they're doing with the system without putting any judgment on whether it's the right or wrong thing to do. So you can encode this, you can encode these facts in this language, say Datalog, although you could also do it in as a graph, as an RDF graph, and in fact that's actually a little closer to what they're actually doing. But you start off with a database of flights that the government has access to, so you know that they bought a flight from Cairo to Miami, and the last name was this, and that it was one way, and that it was on this date. And you also know that they made some withdrawals. There's multiple records here for various amounts from some bank in Russia on various dates. And what I didn't include here was the calls to people in Syria, although I probably should have, because that's perhaps the biggest flag. But you could write that down too. You could say call from this person to some other person where location of the other person is Syria. So these are a representation of all the facts that they have access to. And the point I want to make is that the aggregation of these facts into a alert of some kind, into a this is worthy of further inspection, can be expressed as a query in these various languages. And in particular, I'm going to talk about Datalog here. So maybe you might flag a person, and this number 1 is just a token to say that this is one flag, and this is a date associated with the time that was flagged in case you want to do further analysis. This might become clear in a moment. You raise this flag if a person bought a flight from some origin to a destination where the origin was one of the flagged airports, I'm making this up, and the destination was a U.S. airport, and the ticket type was one way. Obviously this alone is not necessarily suspicious, but it's perhaps a first step, is that from a airport that we sometimes monitor more closely to a U.S. destination, and it was one way. Okay. Then you might build a table of you might express a query producing foreign withdrawals that are the sum total amount withdrawn from a foreign bank where individual amounts were greater than 1,000, because maybe you're trying to cut out small withdrawals. Okay, and so this says, assuming we're building off this withdrawal table, we add up the total for each person coming from a foreign bank. Okay, this could maybe be called big foreign withdrawals instead of just foreign withdrawals. Okay, and then the flags are perhaps associated, well, when the total amount across all these withdrawals are greater than some fixed threshold. Here I've said 10,000. Maybe that represents a flag. And notice that these flags are the same relation as these flags. In Datalog, it's okay to have multiple rules like that. And the semantics of them is you're going to union all these results together. So you can imagine expressing this in SQL as well, where I query for a bunch of records and query for another bunch of records and then union the results together. That's what's going on here. All right. And then we skip the conditions on the calls to Syria, although again, those would be easy to do and probably good examples to include. But maybe we have this database of all the vehicle rentals with attributes, the person who rented it, the vehicle, the origin, the destination, and some kind of a date. And so we write a query producing yet another flag when someone rented a vehicle where the destination was some important location. And this one's probably not the greatest example of something that would generate a flag, but it's something you could look for, and you can imagine making this a little bit more complicated. Okay, and so all these flags together, you can write another query in Datalog. And again, I haven't told you too much about the details of Datalog, but one thing you'll notice here is that I'm using aggregations in the head of the rule, just like you can in SQL. So select person, sum flag, min date, max date, group by person is the same semantics as what I'm showing you here. So we add up all the total flags. Now we have a relation with people, their total flags, and the date range for which those flags occurred. This won't get you exactly the right results because we didn't really filter much on dates, but you can see the argument I want to make is that it's not too much code, it's not too much work to try to express these English questions you have over this massive graph in terms of a logical language like this. Okay, and so maybe finally the alerts, things that warrant more human attention by some analysts, are things where the max date minus min, within the span of just 10 days, the total flag count is greater than, say, 3. And again, one problem I've sort of pointed out with this is giving you the total across the entire range of time for that person. And so you may want to bucket this by weeks or months, and I haven't expressed that here. Okay. So what I'm hoping to do is whet your appetite that these kind of rule-based logical languages can work with a big graph, can work with a lot of relations, and can express fairly complicated conditions. And they're in some sense, they're all you need. If you have a way of implementing this at scale efficiently, this is kind of all you need to do fairly advanced analytics. Okay. So let me give you one more example of a data log query. So we want to know who contacted who and when they contacted them, but we don't really care how they did. And this is a simplification of something we saw in the previous example. So we say person 1 contacted person 2 at some time if person 1 sent an email to person 2 at some time. We also say person 1 contacted person 2 at some time if person 1 called person 2 at some time. And then finally we say person 1 contacted person 2 if they sent a text message at some time. And so the point here is these would most likely come from 3 very different sources, right? As the government is doing whatever they're doing to get email, again, whether you agree with this or not, that's one company or one source. Another source is who called who, and a third source is who sent a text message to who. And so combining all these together doesn't necessarily take a lot of work. You can express these in these high-level languages, and this is, I would argue, the right way to approach these problems as opposed to a lot of low-level code. Okay. So let me give you one more example. Who could have known before June 3rd that some event was going to happen? Maybe you know for a fact that someone named Sam knew. Okay, so you're starting from that point. Well, who else could have known? Well, using this same trick we used in the to build up a contacted relation, you can do this again. Well, we know person 2 knew if person 1 knew and person 1 emailed person 2 before June 3rd. Sorry, that's the other condition we're looking for, right? And we can also argue that person 2 knew, potentially knew, if person 1 knew and person 2 met with person 1 before June 3rd. And so the point I want to make here is that we've referenced the relation that we're creating, new, we've referenced it in the body of this rule as well. So there's a recursive relationship now, right? It starts with Sam, and then basically we find all the people that Sam emailed before June 3rd, and they're in the final result. And then all the people that those people emailed before June 3rd, and they're in the final result, and so on. And you can do this with met, and you can do this with called, and so on. So this recursive relationship, this self-reference, is the difference between Datalog and SQL. You actually can express this kind of thing in SQL. There's Microsoft calls them common table expressions, and you can use the with clause to do this recursive stuff, but you'll find if you try to do this in practice that the implementation of those features is a little bit poor in many of the commercial databases, and there's various limitations. For example, you can only have a depth of 100 recursive steps, which is sort of arbitrary and much too small for many of these applications. You'll also find that the performance of these varies wildly and is not particularly good. So it's not clear that the customers of relational databases have been demanding these features. But I'd argue that increasingly this is what people are interested in. And my evidence is examples like we just saw from the news. The fact that graph-specific database systems are emerging, Neo4j is getting very, very popular. There's various systems for processing graphs on top of MapReduce, and we'll talk about a couple of those, and so on. RDF systems, these so-called triple stores. So the fact that graphs are becoming more and more important suggests that this ability to traverse the graph recursively is becoming more and more important, which motivates perhaps a move from SQL relational algebra languages to this Datalog relational algebra language. And so my prediction is that you're going to see Datalog pop up more and more often in industry. Okay. So let's take a step back and see where we are. We talked about graph tasks in general, gave an example of constructing these histograms, talked about structural, traversal, and pattern tasks, gave PageRank as an example of structural of both a structural and a traversal task, and then talked about pattern languages in SPARQL and SQL and Datalog, gave a few more detailed examples of Datalog motivated by what's been going on in the news in June 2013 related to the PRISM system. But what we haven't talked about is how to implement much of this, especially at scale. So that's what I want to do next. We're going to stick with Datalog for a moment and think about how to actually implement those kinds of queries in MapReduce, and then talk about how to implement PageRank in MapReduce. So way back towards the beginning of the course, we talked about how to implement relational algebra operations in MapReduce at scale, and we showed this sort of connection, between languages like Pig and the relational algebra. What databases do is obviously the relational algebra, and what you can implement directly in MapReduce. So there seems to be this kind of relational algebra DNA in a lot of these large-scale programming platforms. However, all of those cases, we never had anything that had to loop, that had to do recursion, that had to do iteration. And now that we're talking about graphs, as we sort of pointed out, that traversal of these graphs is really the salient feature of working with them. And so it came up in traversal tasks, and it came up in pattern languages in Datalog. We saw examples of recursive Datalog programs without talking much about how they would be implemented. So I want to cover that a little bit now. So given if you have a recursive Datalog program that looks like this, so you can say this is an edge relation that's just linking an arbitrary vertex x with an arbitrary vertex y. Every pair of edges is stored in a relation called edge. And I write this program. This program says, find me all the edges connected to the vertex labeled W, and here we have a vertex labeled W, and put those in a new relation called A. Then also find me additional values of A in this manner. For every vertex that's already in A, go find me an edge that leads out from that vertex and give me a new generation of vertices. So this is now a recursive Datalog program, but what you can think about it intuitively, what it's doing is traversing this graph in kind of a breadth-first way, right? So first we fire this rule, which just says, out of all the vertices, select the one with W. And we know how to do this. We could write this in SQL, I would hope. Right? We can write this in MapReduce. We could write this in Python. Find me all edges where the first position has a label equal to W. And call that A0. Or find me everything that's connected to W, call all those collectively A0. Next we go to this rule, and now we have to join all the ones we've already found with the edge relation to produce a new generation of vertices. For each node in A0, find all of its neighbors. And then in step 2, we fire this rule again. For each node in A1, find the neighbors, and so on. So we keep finding more and more vertices in this graph as we go one generation away. And that's naively how we might evaluate this recursive program. That's what the meaning of this program is. Okay. But there's a problem here. What if there's a cycle in the graph? Well, at generation 1 we'd find Sue, at generation 2 we'd find Tom, at generation 3 we'd find Lynn, and then in generation 5 we find Sue again, and so we would just keep going. So we need one more piece, which is to remove all the ones we've already found previously. So let's look at this again. So this is called semi-naive evaluation. So here's this reachability query that we were just looking at. Find me everybody that's connected to everybody that's in the social network of some vertex labeled A, right? Everybody that's reachable from A. So here's how it would work. We're going to have these delta relations, which are just just everything found in the new generation, right? Just like those colored levels were in the previous pictorial representation. So while we're still finding new vertices, we're going to keep going. If at any point we don't find anything new, then we know we're done, and we can stop and we can return the result. Okay, so while we're finding new things, let's call A to AI the union of all the deltas that we found previously. At iteration 0, union with iteration 1, union with iteration 2, and so on. And if you're not familiar with this notation, this just means, think of it as concatenation in a programming language, right? Except you're also going to remove duplicates. All right. Then delta AI is the previous new results joined with the relation R, right? So this gives me one more generation. And I'm expressing this in the relational algebra notation of join. So that's what we showed pictorially a moment ago. However, now what we also want to do is remove any duplicates. We want to subtract out anything we found in any previous generation at all. And this is in order to break cycles. If we've already seen that, if we already found Sue, then we don't want to find her again. All right. And then we increment this counter so that we can keep track of everything. And then our final result, when we're done, is this AI for whatever I is at the end. And so I'd claim that if we're going to do this in MapReduce, which is what we're trying to build up to, then this line is the important line. This line is actually pretty easy in MapReduce because of an implementation detail. A union of a bunch of different data sets, if they're known to be disjoint, is actually literally just concatenation of the files, which sort of happens implicitly in MapReduce. And I'm not going to go into much more detail than that, but suffice it to say that this line can be arranged so that it's not very expensive. It's essentially free. But this line is where there's a lot of work going on. So let's look at let's break this down and pretend like, and show how this is going to be implemented in MapReduce. All right. So it's actually two different MapReduce jobs, one to do the join and one to do the difference. And we saw this in the lecture on pig, where join was one operation, and we didn't show a pig operation corresponding to difference, but you can implement it using grouping. Okay. But we did see that generally one operation and another operation would turn into two different MapReduce jobs chained together, and that's the same thing that's going on here. So what happens with the join is we have the delta A from the previous iteration, along with the very large edge relation, right? This is billions of edges, perhaps, spread across all sorts of computers. And we process them all in parallel, spray them across the network, and implement the reduce phase in order to compute the join. Then to do the difference, we find everything we just found from the join, spray it across the network again, along with everything that we've ever seen before, everything in this AI, everything in the union, and make sure to remove duplicates. And you implemented both of these things, or specified how to implement both of these things in the MapReduce assignment. You showed how to do a join, and you showed how to do a duplicate elimination, essentially, which is what this is doing. Okay. And then the only new piece we need, which is where MapReduce gets a little bit it becomes a little bit of a poor fit for this task, is that you need some sort of external driver program to control the iteration, to check and see if there's anything new. Okay, so MapReduce can't do loops in and of itself, so you have to do something outside of the system. All right. So again, two big steps: compute the next generation of vertices or nodes, and remove the ones we've already seen. All right. So this is fine, and this works, but there's some performance issues that are pretty significant, and we'll talk about that next time. All right, so if this is the basic idiom for implementing recursive programs in MapReduce, maybe we're done. Well, there's a couple of problems here. And here they are. First, on every iteration, right, we're going to do this over and over and over again as we traverse the graph. And the number of times we're going to traverse the graph is actually the diameter of the graph, which we talked about. Well, on every iteration, we're going to process all billion edges in the graph in the map phase and shuffle them across the network to the reduce phase in order to compute this join. This wasn't so bad if you're only going to do this once, but if you're going to do it every time, there's no useful work happening in this map phase. You're just reading the edges off disk, assigning the key to the, identifying the join key, emitting the appropriate tuples, and sending it across the network to the reduce phase, implementing a standard join in MapReduce, which we did as part of the homework. So this is extremely wasteful. The second point, which is a little bit more subtle, is that the answer set, AI, is growing at every iteration, right? You find more and more answers, and as soon as you stop finding answers, you're done. Well, this is getting bigger and bigger and bigger over time, so it's not completely static. But all the old values that you've already seen before are read off of disk and shuffled across the network in the same way in order to try to remove duplicates. And if you've already done that once, you shouldn't have to do it again. So the solution here is to fill in some sort of a cache on the reducer side of the MapReduce program. So instead of shuffling this across the network, we're going to shuffle it once in the first iteration and then read it off of disk in the second iteration. And with a variant of this trick, you can do the same thing here, where you'll read it off of disk and then append more new tuples back to the same cache right as you're done. And with some careful thought, you can arrange for this to happen within the MapReduce framework. Sorry, not within, but by extending the MapReduce framework, and still keep a MapReduce programming interface. And this is what we did as part of our research for this system called Hadoop, which is to add iterative capabilities to the Hadoop MapReduce system. Okay, and one of the applications that we did with this was to implement Datalog. All right, and so this makes a pretty big difference. So this is a plot of runtime, and this is iteration number. So this is just the time it takes to do each iteration. And without the cache that we just described, every iteration takes about the same amount of time in this particular data set, which was a variant of the same one you processed in the Elastic MapReduce assignment. With the cache, the first iteration actually takes a little longer because we have a little bit more work to do. We have to prepare this cache. But subsequent iterations take far, far less time because you don't have to map and shuffle that huge relation, that huge edge relation across the network anymore. So this ended up being, well, really arbitrarily faster because the more iterations it takes, the better and better, the more and more difference it gets in the overall runtime. With the variant of that trick to also optimize the duplicate elimination step, plus another set of optimizations that had to do with using the MapReduce framework in sort of an intelligent way, we're able to sort of get this pretty horrible performance for raw vanilla MapReduce on iterative programs and get it way down to something that is actually kind of approaching the raw overhead of just running a Hadoop job. Meaning, you do no useful work with the Hadoop job. You just launch a task on every machine in the cluster and do no useful work and then shut down. Okay, and that's what this bottom line is. So what I think the takeaway here is, one is I just want you to internalize that trick, but the other thing is if you're using raw Hadoop, if you're using, I shouldn't say raw, if you're using MapReduce right out of the box, it's not great for iteration, mainly for this reason. There's actually a few other optimizations we explored in a couple of papers, but this is the one that makes the most difference, is the fact that there's invariable, quite frequently there's going to be loop invariant data that you need to process, and just to wastefully reprocess it on every iteration turns out to be a killer. Okay, and then one more point I want to make about this before we move on is that the number of new tuples discovered, the new results discovered on every iteration tends to have a pretty standard pattern, which is a result of the degree distribution of common graphs found in practice, which we talked about in the histogram segment a little while ago. So this plot is on the y-axis is the number of new results discovered, and the x-axis is the iteration number. And what you can see here is that in the first few iterations, you quickly start to find an enormous number of new results, right? And notice this is a log scale, so this difference is really, really huge. But then pretty soon it tapers off, and you're just kind of piddling along, finding smaller and smaller sets of new results, but you're not done yet either. You're still finding new stuff, but you're not finding much new stuff. So this is really, really rough for MapReduce, because every one of these iterations, way out here in this long tail, this end game, as Efrati and Ullman called it in a paper, you still have to pay the overhead of launching Hadoop on a huge cluster and sort of processing and checking for things, even though you don't actually find that many more results, right? Most of the results you've already discovered. So, fine, that's one point. The other point here is that this does make sense, because what you're doing is you quickly get to this, within a few iterations, you're going to get to this middle part of the graph that's connected to everything. And the fan out is huge and you've discovered everything. You're going to hit one of these really popular vertices that's connected to everything. And then once you're past that, you've pretty much seen everything you're going to see and you quickly taper off. Okay. So one thing to think about is what to do about these two different regimes you're in. One regime where you're doing a lot of useful work, and one regime in this end game where you're not doing very much useful work. And there's a couple of things you can think about here. One is, it may not be unreasonable to just stop processing when you are no longer producing that many results. This would produce the wrong answer according to the program, but it might be reasonable in a lot of cases. If you're mostly looking for an approximation, you can get a pretty good approximation after the first several iterations. This extra work is not doing you that much good. Another approach would be to scrap MapReduce and try to find something that had less overhead on a per iteration basis. And so there's a system that, for example, we're working on now that doesn't have this property, right? The runtime is sort of proportional to the number of tuples discovered, as opposed to having this very large fixed cost just to launch a job at all, which is a problem with Hadoop. Still another way is perhaps to change strategies. In this regime, you process it as we've described. In this later regime, you actually might try to do more work per iteration. For example, don't bother checking for duplicates, because you're only finding 100 new tuples anyway. Why bother even checking for duplicates? Just keep going and going and going and going for a while to save the number of MapReduce jobs you have to do. And so we've explored these various options, and they all work to varying degrees. Okay. All right, I want to give a quick aside on representing graphs. We've sort of been assuming implicitly that we're representing graphs in this way, with a table with two columns, one source and one target, maybe some other columns representing, for example, an edge label. But every edge would be explicitly represented. Okay, and so this makes sense because it's easy to manipulate with a relational language, which is what we've been sort of talking about in terms of pattern matching tasks. And so this is the edge table. We'll call this the edge table representation of this graph here, where A and B is there and B back to A is there, and so on. Okay. And you can process this, as we've seen. We can do pattern matching, but we can also do the structural tasks pretty simply. We can say find the top 5 highest in-degree vertices using a group by query. Right? From this edge table, for each target, count up the number of sources, group by target, and then select the top 5 from that. And this is using the syntax for top 5 from the SQL standard, as well as Microsoft SQL Server. Other commercial databases can express this in a slightly different way. Okay. And you have to order by the in count here, which is why we do this as a nested query. So fine. So this table gives us a lot of flexibility in how to process it. But there's some costs that we bear to do this. And so what you actually see more often in programming language libraries for working with graphs is an adjacency list representation. And so for each source, each source is associated with a list of all the adjacent vertices. So here with A, you'd be associated with a list of the vertices B and F. And B would be associated with the list A, D, E, and F, everything that's one hop away. Okay. And so the overall space required for this representation is less, which can make a pretty big difference in performance. So as an example of how to use this representation, you can think about a MapReduce program. It's a little bit harder to think about how to do this in a relational database, for example, because you can't, directly and naturally, you can't express this list construct. There's various extensions and proposals and so on to do this, but this essentially it breaks first normal form, which I won't go into, but it's no longer really a conventional relation if you have this nested collection structure as one of the values. But in MapReduce, this is perfectly fine. We saw this before, right? There's a key and a value, and the value can be anything. It can be a bag of words. In this case, it's a list of neighboring vertices. And in fact, in the libraries for MapReduce that work with graphs, this is the most common representation you'll see. And in fact, even in some of the original work with MapReduce to express PageRank, which we'll talk about in a bit, they assume an adjacency list representation there as well. So For this same task of finding the top 5 highest in degree vertices, you can imagine a map program that takes in a vertex and adjacency list and produces a key of the adjacent vertex along with the key vertex. So you just reverse the direction. Okay. So for B and F, the output would be B mapping back to A, F mapping back to A, and so on. And we just reverse the edges. And then on the reduce side, it'll receive a list of a vertex along with a list of incoming edges. And then you can just count them up and produce that as your result. Excuse me. You can count them up and produce that as your result. One final step is to take the top 5, which would actually be a second MapReduce job. So the last representation you'll typically see is an adjacency matrix. And this is really only useful if you have a fast, efficient representation of matrices and you're trying to manipulate the graph as a matrix. But these things exist, and the other nice thing about this is it sort of exposes the equivalence of a graph and a square matrix, right? So a square matrix has all same number of rows and columns, and so how to represent a graph as a square matrix is for each row corresponds to one vertex, and each column corresponds to one vertex, and you put a 1 in that cell if vertex row is adjacent to vertex column. Okay. And if you have an undirected graph, then this will be symmetric. And if it's a directed graph, then it may not be. So A is adjacent to B, which is why there's a 1 here, and B is adjacent to A, which is why there's 1 here. But B is adjacent to D, and D is not adjacent to B. Okay. And you'll also see that this is pretty much always going to be a sparse graph, right? Lots and lots and lots of zeros. Not everything. It's rare for all vertices to be connected to almost everything. Okay. So you have sparse, and if you remember back to some of the work we did with relational databases, and we showed how to represent matrices in databases, that once you have a matrix, you get access to processing things with linear algebra, and you might get access to fast libraries that already know how to work with matrices and linear algebra operations. But what a lot of those libraries do under the sheets is take a sparse matrix and represent it in a way that doesn't require you to actually materialize all these zeros. And those sparse representations are going to look a lot like the previous 2 representations we just saw, an adjacency list or an edge relation. So in some sense, it's, you know, you're moving things into matrices in order to get the access to fast libraries for working with matrices. But what the matrices are doing underneath the sheets is to represent things in a sparse way that looks more like a relational representation. But be aware of all 3 of these: an edge table, an adjacency list, and an adjacency matrix. So we showed how to implement loops in MapReduce and optimize them, and use that to implement the data log pattern language and recursive programs in that language. And we showed different representations of graphs, and now we're going to show PageRank in a couple of different ways at scale. So remember, the context here is that graphs are getting bigger and bigger and bigger. So you can imagine a social scale graph having about 1 billion vertices, 1 per person, with maybe 100 billion edges. Web scale graph is bigger because there's more web pages than people, so maybe 50 billion vertices and 1 trillion edges. But there's the human connectome, the neural network in your brain, has maybe 100 billion edges and 100 billion vertices and 100 trillion edges. So we need large-scale systems to process this, and MapReduce is one such system. There's more coming down the pipe, though, so MapReduce is perhaps on the tail end of its utility for these massive, massive scale, but we're going to stick with it for now. So here's an implementation of PageRank in MapReduce. In the map function, we have a node ID and a vertex object. That vertex object has a couple of methods that we use. You can get its current PageRank, in.PageRank, and you can get its adjacency list, in.adjacency list. So in.PageRank divided by the length of the adjacency list gives us the fraction of the rank that we're going to distribute to each of our neighbors across each of our out edges. Then we're going to emit a special key value pair with the node ID and the vertex object, and I'll come back to that in a bit. And then for each of my outgoing neighbors, send the appropriate fraction of my page rank, which is the value p that we just constructed. Okay, so now on the reduce side, we've got a node ID m and a list of things. Then we initialize a couple of values, this m object to null and a new rank to 0. And then for every p in this list of p's, we're going to check to see if it's a vertex. Now why that's there is if it is a vertex, that means it corresponds to this key value pair that we emitted up there. And all this was a way to pass that complex vertex object through to the reducer. Because remember, the key here is just a node ID. So we need some way of passing this more complex object with some internal structure over to the reduce side. And so now we have it and we assign it to m. If it's not a vertex, then it's one of these other page rank values that we computed, and therefore we just add it up. And then finally, the new page rank for that vertex m is going to be this formula that we saw. Well, sorry, I guess I'm being a little glib there. This is the damping factor that we mentioned, and this is a equivalent expression to what we showed before. And finally, now that we've constructed the new page rank, we emit a key value pair, the node ID and the vertex object itself, which is the same key value types as we need on the map side to repeat this. So we're going to run this over and over and over again with across multiple iterations. So there's some problems with this implementation. The main one is that the entire state of the graph is shuffled on every iteration, right? That little complex vertex object that includes within it the adjacency list associated with that vertex is sent across the network over to the reduce side and handled by the reducer. When all that really needs to be sent is just the new rank contributions, if the vertex state could sort of stay in place. You know, if you could address the neighboring vertices directly and just say, hey, here's your new rank contribution, that would be useful. That would save some communication traffic. Okay. And then also we have to control the iteration outside of MapReduce, including the termination conditions and just the logic itself. So for these reasons, and just to explore another programming model, Pragle was suggested also at Google in 2010. So since then there's been open source implementations just like there was for MapReduce and Apache Giraffe, Stanford. There's a system called GPS, a system called JPragle, Hama. And this is really designed for batch algorithms on large graphs in particular, so focused on graphs. And so the basic logic looks something like this. It says while any vertex is still active or the max iterations have not been reached, for each vertex, process all the messages you get from your neighbors, update your own internal state, and then send messages back out to your neighbors. And then maybe set the active flag appropriately. You know, if you don't get any messages, then you're not active. Or if your internal state doesn't change enough, you're not active. And you can control this logic. And so the point is now you're writing, instead of writing a map function and a reduce function, you're essentially writing just one little function, which is the function that I should run on each vertex at every time step. All right, so let's see an example, which is PageRank. Okay, so there's just one method here, compute, and this is this code is a little awkward. This is straight from the Pragle paper. It's a little awkward here because it's in C, so bear with me if you're not used to looking at C. But this says if basically the iteration number is greater than or equal to 1, the super step, then add up all the messages I get from my neighbors, and then assign my own internal state to this new calculation, to the new rank. Then as long as the super step is less than 30, which is our, you know, if we go over 30, we're just going to assume that we've converged and just quit. Then send the contribution of my rank to all my neighbors, which is my current value divided by n, and n is just the number of neighbors. Otherwise, set myself to inactive, which is this vote to halt. So you sort of say, I've got no more work to do. I'm done until somebody wakes me up with a new value. Okay. And what's not in here in this implementation, but is often added in a Pragle implementation, is some kind of condition that says, well, if the internal value hasn't changed by a large enough amount, then vote to halt, then set myself to inactive. All right, so let's see how this works, because I'm not sure, the code may or may not be very clear. So imagine we have a graph like this. We initialize the rank to the total number of vertices divided by the number of the number 1 divided by the number of vertices. So there's 5 vertices, so we just divide 1 by 5, which is 0.2. Okay, so that's the initial rank. Then the compute program runs on every vertex simultaneously in parallel, and it sends its rank contribution to all of its neighbors. So this rank contribution of 0.2 divided by 2 outgoing edges, so that each one gets 0.1. And here there's 3 outgoing edges, so each one gets 0.066, and so on. Then on the next super step, all those contributions are added up. And so here we add 0.1 and 0.066, multiply by 0.85, and add in 0.03, because that's our formula. And we get 0.172. And we do the same for all the other nodes. Now, this one's a little funny. Why did this node and this node get 0.03? Well, that's because they have no incoming edges at all, in which case this term in the formula provided nothing. Sum was 0. And so they just get 0.15 divided by 5, 0.03. Okay. And so that's our new value after that iteration. Then it repeats. This rank is divided in half, 0.015 and 0.015. This rank is divided in thirds, 0.01, 0.01, 0.01, and so on. And we see what changes. So we add this up, this plus this times 0.085 plus 0.03 gives us 0.0513, and so on. And then I've marked these vertices as red because their value didn't change from one iteration to the next. And so they're marked as inactive. And that condition actually wasn't in the code that I showed you, but it's typically a condition you add. Okay. And so then the process continues. Here's the new values for the next iteration. We start over again. One optimization here is that these messages aren't actually resent. Again, they can be retained on the receiving side. You know, all the incoming edges have a value, and it doesn't necessarily need to be resent across the network. You can just sit there until it's updated. So if this vertex were active, it would be resent with a new value, but since it's not active, you just use the old value from the previous iteration, and nothing needs to be sent. All right, so we recompute these, but we find out that this top vertex didn't change from one iteration to the other, so it goes red. And then these two values are updated appropriately. And that's our new values for the next iteration. And then finally, remember all the red nodes all the red vertices don't actually get executed at all. And so they don't send any messages and they don't send any messages. Nobody needs them. But this vertex still needs to be updated. And so we apply it again, and then finally the execution halts when all the vertices are inactive. Now, it might take quite a while to converge, in which case, remember, there's that super step less than 30 condition as well. So you don't really need to in general, PageRank starts to get pretty close to converging after some number of iterations. You don't really need to let it run for too long.